Okay. So let's continue the relative stability criteria. So in the previous class, in the previous class, we had the relative stability criteria. I don't know what's happening here. Okay. So now let me finish that. Oh my God. Okay. Let me finish that by our famous example that I taught you in the first class. If you have such a transfer function, s square plus omega square. Do you remember that which transfer function for which physical system it was? Do you remember? It was for the pendulum. Remember? Here was omega n square. Say omega n square. Okay. So it was pendulum, first class. Pendulum. So based on the relative stability criteria, you have s square, s1, and the s naught. That's right. So here you're gonna have 1 omega n square, and the last line is the omega n square, as you know. So what's gonna be here? S power of 1. Come on, guys. What is that? From what I taught in the previous class. What is here? The first and second line, they are coefficient of distance, right? So gonna be s square plus 0s plus omega n square. Now what is here? What is here? Yes. So, guys, remember the pendulum, that's right? Pendulum, what was the response of the pendulum in time domain? When we had a pair of, what? Yes, yes, it was oscillating forever, right? So we had a pair of the poles was plus minus I omega n. So right, a pair of what? A pair of pure imaginary poles. So this is the final case of the relative stability criteria by saying that if you have 1, 0 here in any line, and the above and the below that is positive, there is no sign change, it's an indication of that you have marginally stable system. Marginally stable system. So we're going to use this in designing the PID controller in the Nichols-Ziegler criteria for the PID controller. So if you have 1 only 0 here, not the rules of the 0, 1 only 0. And above and below that is positive, no sign change. Your system has a pair of complex conjugate poles. Or has a pure imaginary poles. Or a pure imaginary poles. Okay? So now, these days, by having MATLAB, determining the stability or instability of the system by the relative stability criteria is kind of ridiculous and funny. So why we are using that? Because of this. Suppose that you have a second order system. Y over x is 1 over s squared plus k1s plus k2, right? And these are the parameters of the system that we don't know. So we want to find for which range of the parameters your system is stable. Again, what you're going to do, you're going to make this row stability criteria. Going to be 1, K2, K1, and the last one is K2. Based on the row stability criteria I taught you, you know that the first column must exist, non-zero, and be positive. So it says, whatever your system is, second order system, master spring damper, I don't know, the tank of the fluid in series, the RLC circuit, whatever it is, a robotic arm, just single robotic arm, okay? So the stability says that K1 must be greater than 0 and K2 must be greater than 0. And this is valid, remember? This is going to give you 3 cases of under-damped system, critically damped system, over-damped system. Now, if one of them is negative, like y over x is, say, s squared minus 2s plus 1, see that k1 I say is negative. This is going to be s minus 1 squared. So you have 2 repeated poles real in the right hand side of imaginary in the complex plane. Imaginary real. That's going to be plus 1. So you have 2 repeated poles here. And I taught you that your system is unstable here. Unstable here. So row stability criteria says for this system, where K1 and K2 must be greater than 0 for stable system. Clear? Right? Now, let's go to other system. Y over x, I'm going to have 2 examples. Say is 1 over s cubed plus k1s squared plus k2s plus k3. You have a third order system. And you want to see for which range of decays your system is stable. Okay, so we're going to have s cubed, s squared, s1, s0. So you're going to have 1, k2, and there's nothing, 0. You have k1, k3, nothing. You know the last line is k3 based on whatever I taught you. So here is k3. So S1 is this multiplied by this minus this multiplied by this divided by 1. So I'm going to K1, K2 minus K3 divided by K1. So based on the rough stability criteria, the first column must exist and be positive. Obviously, K1, based on the first condition of the row stability criteria, K1 and the K2, remember, and K3 must exist and must be positive. This is one condition. Now, based on this, okay, K1 must be greater than 0 from here. K3 must be greater than 0. And now, from here, K1, K2 minus K3 divided by K1 must be greater than 0. We know that the K1 is positive. from here. So this also must be positive. So say K1, K2 must be greater than K3. So the stability condition for this system is K1, K2, K3 must be greater than 0, and K1, K2 must be greater than K3. Okay. Let us select some numbers. Let us say K1 is 1, K2 is 4, and K3 is 2. So first condition satisfied. Second condition, and if K1, K2 is 4 greater than 2. Bingo. Let's go to the MATLAB. Okay. I want to show the both cases. Okay. Is 1, 1, 4, 2. So what I'm gonna do, I'm gonna define num is equal to third order system 0, 0, 0, 1, and then is 1, 2, because that's 1, 2, 1, 1, 4, 2. Sorry, 1, 1, 4, 2. Now I'm gonna plot the step response of this num and then based on the stability criteria. Here we go. System is stable. It's under, down, and stable. Okay. So, but if I change terminate, if I terminate the condition saying that, okay, you know what? I'm gonna select this time K2 as 1. So now K1 and K2 is 1 is smaller than 2. K2 and K1 is 1. So I'm gonna change K2 to 1. Got here, guys? I'm gonna say then this time is 1. Now if I plot, it must has unstable behavior based on the rules of stability criteria. It is, see, unstable. See the amplitude to the power of 1026. So you see that based on rules of stability criteria, you can determine the domain of stability for the linear systems. So having that, if I say sims x, I want to find the poles of this system. Okay, I'm going to say solve x cubed plus x squared plus x plus 2. I expect to see right hand side poles. Oh, double n's. As you see, we have a right-hand side faults, a pair of complex right-hand side faults. So we did a Roth stability criteria. If you are not certain of the system parameters, dynamics can give you that where system is stable and where system is unstable. See what I'm saying? Yes? So let me go to the last example here, higher order systems. So it says, for example, if y over x is 1 divided by, this can be spring mass damper in series, okay? S4, fourth order system, plus K1 plus 2 S cube plus 2S square plus K2 S plus 10. Now, based on the Roth stability criteria that you know how it works, the first condition is that, as you see here, that K1 and the K2 must be greater than 0, no doubt. The second is that S4, S cube, S square, S1, and the S naught. So you know that here is 10. Here is 1, 2, and 10. Here is K1, K2, and 0, nothing. So the next line gonna be this multiplied the 2K1 minus K2 divided by K1. Next time is this multiplied by this minus 0 divided by K1. It's gonna be 10. Clear, everybody? K1 10 minus 0 divided by K1 10. Next line gonna be this multiplied by this, so you're gonna have K2 2K1 minus K2 divided by K1 minus 10K1 divided by the same number. I'm going to say A. Okay. A. Okay, so based on the Roth stability criteria, you know that the first line must exist and be positive. Here we go. So from here now we know that the K1 must be positive. Good. Now this must be positive. I'm taking out here. So 2K1 minus K2 divided by K1 must be positive. Because already K1 is positive, this must be positive. Being said, from here, we get that 2K1 must be greater than K2. Here we go. Here we go. Now, this must be positive. Because already this is positive, so A is positive. We don't care. So you get that K2 in 2K1 minus K2 minus 10K1 divided by K1 must be positive. I'm in the numerator. So this is gonna be a square if I do that. See here, a square, because K1 already is positive from the first condition. So this must be positive. This must be positive. There we go. So you see that the K2 in 2K1 minus K2 must be greater than 10 K1 square. Here we go. So you see the stability conditions for this fourth order system is K1 and K2 must be positive. 2K1 must be greater than K2, and K2 in 2K1 minus K2 must be greater than 10 K1 square. Clear, everybody? So let us select some numbers. These are the stability criteria for this fourth order system. Stability criteria. Let us say K1 is 5, K2 is 1. Just select number. So the first condition satisfied. Second condition satisfied because 10 is greater than 1. Let us try this. So K2 is 1, 2K1 is 10, minus 1, greater than 250. 250? 9 is greater than 250? Yes? No. So this number leads to instability, guys. Look at here. If I say, let's go to the MATLAB. By selecting this, 1, 5, 2, 1, 10. If I say num is 0, 0, 0, 0, 0, 1, fourth order system. Then is 1, 5, give me the numbers. 1, 5, 2, 1, 10. And 2, 1, 10. Oh, num is okay. So now if I say step now and then, it must show unstable system. As you see, it's unstable system. 10 to the power of again. So you see that you are not allowed, you have to select. So I'm giving you now as a class quiz. Select K1 and K2 that this third condition is satisfied, guys. Select K1 and K2, I give you 5 minutes. Does this be satisfied? Go ahead. Any set of numbers you could find? Any guess, guys? Oh, we have a chat. Not yet. Okay. Find K1 and K2 that satisfy this condition. This condition. Yeah, sure. So let us ask this, please, at the end of the class, okay? Sure. Okay, guys, so if you cannot find, please do it as homework. And maybe there is no such a number that satisfy this. Try at home, okay? Maybe there is no such a number. Okay, so let's continue. But let me give it a try before going ahead. So let me select K1 as 0.5 and K2 even as K1 as 0.75 and the K2 as 1. Even that I select this, you're gonna have 1.5 minus 1 greater than 10 K1 square, 0.75 square. How much is that?
7.5.
No. No. Use a calculator. How much? There we go. It's not valid anymore. So, as homework, see if you can find K1 and K2 that satisfy this. If not, means your system is not stable for any value of the K1 and K2. If not. See what I'm saying? Another approach is that you select a number, say K2 is, I don't know, 1. Okay. Then say, okay, K2 is 1. I'm putting here. So you're going to have 2K1 minus 1 greater than 10K1 squared. Do we have such a number? Do we have such a number, guys? Or you select this, K2 is 20 this time. So you're gonna have 20 this, 20 this. So the result is 2K minus 20 to K1 greater than 0.5 K1 squared. Do we have such a number? Try this like that, okay? Okay, so having the root stability criteria, okay? Now let's go to designing the controller. So PID controller. Okay, let's go from basics. I'm gonna take you back to the class 1 of this semester. I taught you intentionally because I knew that at the end of semester I'm gonna back to this. LM pendulum theta. So if you apply torque here, control torque, I'm applying a control torque here, or U. We're saying that control input U of t. And my intention is that to keep, for example, at set point of theta naught of 45 degree or pi over 4. But I knew that from the first class, theta of s, if you look at your notes, over U of s is is 1 over s squared plus omega n squared, for example. Okay. Okay. So this has a pair of pure poles, pure imaginary poles, and P1 and the P2 is plus minus I omega n. Guys, stop me because this is the most important part of the course after this. Real, imaginary. So you have two poles, and that's why your system oscillates forever. Plus I omega n minus I omega n. So I told you what's your function as control engineer? To move everything from the left hand side, imaginary poles, to the left-hand side, the poles of the system. So, you know what? So let us do this. Let's go now to block diagram. Because I'm going to do in MATLAB and encoding eventually to teach you what is PID controller. Now we have controller here. C controller unit. And this is going to send you a U, right, to the plant. What's the plant? This is open loop transfer function. Open the loop transfer function. Okay, it's going to be 1 over S square plus omega n square. This is going to give you this theta of S. But our desirable, let me say desirable, theta that you want to follow is pi over 4 step function. Through an ideal sensor, it's going to be feedback to this. So what was the name of this signal I told you? This signal? Come on. Error signal. Which is the error signal, as I taught you, was theta d, desirable angle that you want to keep, minus the real angle that is coming out. And what's one of your function is that you make the error signal to 0. Means you wanna this real angle eventually becomes the desirable angle. Okay. And based on what I taught, you know, theta over u is pendulum, open loop transfer function. So now let me focus on this design and control. Okay. So if I say u over e error signal transfer function of the controller is kp, constant number. First of all, guys, you tell me, based on the Ross stability criteria, by looking at this transfer function, your system is stable or unstable? Why? Because lacking, I just told you, lacking what? Yes. So if you want to make it move from the imaginary axis to left hand side, means that make the poles in the left hand side, you have to add one S here. Okay, so this is first condition I told you. So transfer function of the controller u over e is kp, means a constant number, means proportional in controller. Okay, great. Proportional controller or P controller. Okay, let's do that together step by step. Let's see what P does. Let me do this. I'm just putting KP, P controller. If I do that, you know that this block diagram, please stop me whenever you don't understand. This is gonna be like this. Desirable angle plus minus. Now Kp S square plus omega n square theta this. Now if I want to, this is your G, your new G, open loop transfer function. So theta over theta d closed loop transfer function gonna be Kp s square. You know that this is equal to G1 plus G. Now you know it. Plus omega n square plus Kp. So what happened? I only added the proportional controller. What changed, guys? What changed? What changed of the system? Based on whatever I... Now, what was this? I want that you tell me. What was this? Omega... Yeah, natural frequency. So by adding only a PID controller, you are just tuning or changing the natural frequency of the system. See what I'm saying? Yes? So did we add S here? Did we? No. So as you can say, can I go to next page? Yes? Okay, you can say P modify transient response of system. Only P controller, because changing natural frequency. It's only changing natural frequency of the system. P modifies transient response of the system. Only single P. Okay, I'm just only single P. Okay. Now, let me add this. Let me add now. I say controller transfer function U over E is Kp plus KDS. When I was teaching you at the beginning of this semester about the S, what does this mean in time domain? Laplace of which function gives you S? Yes, this gives you S derivative. So this is PD, proportional derivative. This is derivative proportional. So this is derivative controller, PD controller. Okay, so now this time I'm putting Kp plus KDS. So if I do that, your block diagram becomes like this. You are multiplying this by this, right? As I told you. Gonna be Kp plus KDS divided by S square plus omega n square. This is gonna be real theta. Here we go. And this is your new G. So the closed loop transfer function by adding PD controller gonna be G1 plus G. So you're gonna have Kp. If you do it at home, I'm just skipping that. Gonna be S square plus KDS plus omega n square plus Kp. Let me change the colors. KDS Kp. So what happened when I added PID controller. What emerged here? S. Yes or no? Huh? So I stabilized the system and I tuned the natural frequency of the system by Kp. So you can say the controller function is to stabilize a system given. And the PD is to stabilize and tune transient response of system. Okay guys, you're gonna tell me, Payman, why you say now again transient response. Guys, do you remember this when I was teaching you second order system? Hold on. Do you remember this when I was teaching you second order systems? This was 2 zeta omega n. Kd is 2 zeta omega n. Natural frequency. You see, Kd is affecting the damping ratio of the system and the natural frequency. And Kb is affecting also natural frequency. And remember, when the system was under damp, the overshoot was a function of zeta. Remember? Yes? And settle and the time of the peak was this. Tp was pi over omega d. Omega d was function of zeta and omega n. Remember? So you see that the PD is stabilizer because adding S and tune transient response. Clear, everybody? Yes? Huh? Yes. Good. Now, before going to the I want to give you example. Okay? Exactly based on this. When you are done, let me know. Good. So guys, by having the example of the pendulum, I'm your boss. I'm telling you design a controller for me, PD, that gives you your system be under damp, your pendulum. For example, your system be under damped with maximum overshoot of 25% and peak time of 4 seconds. What's my, when I'm paying you as a control engineer, I'm saying you design the controller for me. Design the controller for me. Knowing that pendulum, by assumption there is no friction, the hinge joint is marginally stable. Okay, so what we're gonna do? Simple like that. We got theta over theta d desired is, what is that? Kp plus kds after we design controller, s square plus kds plus omega n square plus kp. That's fine. So we knew that the KD is, based on whatever you learned here, KD is 2 zeta omega n. And you know that Kp plus omega n, let me say omega n1, meaning that new natural frequency, is equal to omega n1 square. Based on this, remember? Based on this, comparing this with this. So your boss says, I want to have maximum overshoot of 25. So overshoot 25% means 0.25. Based on whatever I taught you is E minus zeta pi 1 minus zeta square. From here, so you can easily use MATLAB or your mathematics from high school and calculate zeta. Peak point is 4 seconds, boss says. Peak point is 4 over is pi over omega d. Pi over omega n 1 minus zeta square is how much your boss says? 4 seconds. When you got omega from here, you can calculate omega n from here. Bingo. Okay. I mean omega n1. That's right. So now you can calculate KD from here. 2 zeta omega n1. And you can calculate Kp from here. Because this is what? This is G over L. Remember? G over L? Gravity over length of the pendulum. I put here omega n1 minus this, gonna be your Kp. So your controller gonna be some numbers. Okay? Everybody understand? Yes? Okay, write it down here because omega n1 squared is all of that. So now, after Kp and Kd, you design your PD control. Yeah, that's it. I want to stop here and before going to the eye controller. And then I'm going to judge why we say PID. Okay? Everybody understand? Yes. Yeah, no, they are the same. They're misplaced. And one. Sorry. So let me first stop it.